Hi everyone again. So welcome to our third lecture in physics. Okay, so we are doing the chapter current electricity. So far what we have discussed is the types of flow, right? And from that we understood the concept of internal resistance of the cell, and we discussed the formula for EMF, PD and loss, and we solved a few numericals for that, right? Okay, so just to revise a little bit in detail, so we have two types of flows, natural flow and the artificial flow. Okay, natural flow is always from high to low, artificial flow is always from low to high. Okay, and natural flow is automatic, it happens on its own, and artificial flow, right, some external energy has to be given, otherwise this flow is not going to happen. Okay, so what we can do now is, you see, the natural flow can be further classified into two types. Okay, so let's understand that today. Okay, so natural flow, which is from high to low. Okay, so please note that both these flows are going to be from a high level to a low level. Okay, so the first one is called as diffusion. Okay, so you might have heard this word before. Okay, it's a very common word. You will see this word also being used in some chapters in biology and chemistry as well. Okay, diffusion, and the second word is drift. Okay, so let's understand this simple example. Okay, so I have a container with water. Okay, and let's just see what happens. So there is a drop of ink which falls into this water, and see what is happening to the ink. Can I say it is slowly diffusing out? It's just spreading out slowly into the water, right? So this is what I call as diffusion. It's a very slow flow, right? And again, it is from high to low. Where the ink falls in water, the concentration of ink is high. Everywhere else in the water, it is low. So the ink is just slowly spreading out. It's flowing, right? I'm talking about the flow of the ink. You could see it. Okay, so it is a flow from high to low, right? But it is a very slow process. Okay, and what about any external energy? If you see here, in artificial flow, external energy is needed, okay, without which this flow is not going to happen. But this is a natural flow, so artificial energy is not needed. Okay, and it's not given. It's not needed, it's not given. So that's the meaning of diffusion. Okay, and let's see this example now. So again, this girl is having a container of water, and she is putting a few drops of ink into the bowl of water, and let's see what she does next. So you can see the ink slowly here is diffusing, right? The ink is spreading out into water. Okay, and then just see what is she doing now. She's taking a spoon and just stirring the water. Okay, and then you can see again there is a flow of the ink, but this time it's much faster, right? So this is what we call as drift. Okay, drift means again it is a flow from high level to low level. That means the ink is flowing from a place where the concentration of the ink is high to a place where the concentration of the ink is low, but this time it's going to be much faster. Why? Because some external energy has been provided, has been given. It's not that the external energy is needed. You see the difference between artificial flow and drift or diffusion, whatever it is, it's a natural flow. Okay, here in drift, artificial energy is not needed. So if you don't give this energy, what is going to happen? Okay, if you don't give external energy, very simple, it will turn to diffusion, it will become slow. If she would not have taken that spoon and just stirred up the water, okay, what would have happened to the ink? It would still have flown slowly into the other regions of the water, of the container. So that's the idea here. In drift, the flow becomes, the diffusion becomes faster, right, by providing some external help, some external energy. In this case, right, the girl was using her hand and stirring up the water. Okay, another example. So you can see these right? People, they are doing they are skiing, okay, over ice, over snow. So you can see very clearly that they are going down the hill, right? So I can say they are flowing down from high level to a low level. They're just going down the hill, okay? And if you notice carefully, you see these people, right? They are also being transported up the hill again, okay? So they will go up the hill and then they will, just smoothly ski down. So was there any external energy provided? Okay, no, I can just say this was like a flow from high to low, natural on its own, and it was drift. Okay, but look at this man. Okay, he's on a snowmobile. What's a snowmobile? Right, it's like a small car kind of, or a bike, a machine on which this person is riding, and you can see carefully, if you notice, it is also a downhill. Okay, so if he doesn't turn on the engine, if he doesn't turn on the motor of this snowmobile, what's going to happen? He's just going to diffuse down the plane. But if he turns on the engine, he's giving some external energy in the form of the chemical energy of the fuel which is being used up, right, in the motor, which is generating the extra force, right? So in this case, he's not going to diffuse or just smoothly slide down how the previous case was. He's going to go down with a higher speed, right? And I can call it as drift again, right? So again, let's take a bottle of perfume, okay, third example, and I just open up the cap. So what's going to happen, right? You will be able to smell the fragrance throughout the room, okay? So if you're sitting in a room and a bottle of perfume is opened up, say you are in one corner of the room and in the other corner of the room this bottle of perfume is opened up. So what's going to happen? Maybe I would say in 30 seconds or so you would be able to smell the fragrance, right? So can I say there is diffusion of these perfume molecules throughout the room, right? There is diffusion, okay? And it will take maybe at least half a minute for this fragrance to spread out throughout the room, okay? Now if I want to speed up this flow, so again it's high to low, high concentration to low concentration. If I want to speed it up, what will happen if I turn on the fan? So once the fan is turned on, right, what will happen? It won't take 30 seconds now for the fragrance to spread everywhere. If the bottle is opened up with the fan above you turned on, then maybe in 10 or less than 10 seconds the fragrance can spread everywhere throughout the room. Okay, so again this is an example of external energy is being given, and because external energy is being given, right, the flow, right, it is still high to low, it's becoming faster. Okay, it's not needed, as I said, it's given but it's not needed. If it's needed, then it becomes an artificial flow. So it's not needed. Okay, if you don't turn on the fan, the flow is still going to happen, but it will be diffusion, it will be slow. Okay, so what about our example? We are in the chapter current electricity. So say we have this cylinder here which represents our resistor, okay, and there are some electrons inside. Okay, so what is happening to all these electrons? Can I say they are just randomly moving? So you can see I've just drawn a few dots here, and they're just randomly diffusing, into different areas of the resistor. Okay, but now what will happen? Okay, so diffusion is random here. If you notice, the diffusion of the electrons is random and there is no net current flowing. The electrons are moving. Metal always has free electrons, okay, and the free electrons, they always keep on moving here and there. So there is diffusion, there is no net flow of current. But what if, right, so this is diffusion, what if I connect a cell now? So if I connect a cell, what is going to happen is, you will notice these electrons now will start moving in a fixed direction, and their speed also will increase. Okay, earlier they were just moving randomly, now it is a fixed direction, and this is what I will call as drift. Okay, the electrons are drifting from, I would say, the negative terminal of the cell to the positive terminal of the cell, right, flowing through the resistor. So in this case of the drift, okay, the speed is going to be slightly higher. Okay, and why are they drifting? What energy are we giving here? Okay, so please note that there is something called as an electric field. Okay, these electrons are being placed in what we call as an electric field. Just like if I take a magnet, then the space surrounding the magnet, okay, it is called as a magnetic field. So what do we mean by magnetic field? In this field, if you place an iron particle, okay, a small iron particle is placed in this field, then that iron particle is going to experience a force. Okay, that's what is called as a field. If I have a magnet in one room, a small magnet in one room, and the iron particle is in the other room, okay, it's not going to experience any force, right? Because the particle is not in the field. So similarly here, instead of a magnetic field, okay, you are going to talk about what we call as electric field. I'm just giving a very brief introduction on this topic right now because it is studied in detail, in depth in the chapter known as electrostatics, which is again for our 12th standard syllabus split into half. Okay, half of the chapter is in 11th and half is in 12th. NCRT, the entire chapter is in 12th. It's just like current electricity. So what is this concept of field? You see the left end of the resistor is connected to the positive. So I can say, okay, this side of the resistor is like the positive terminal and the other side, okay, is connected to the negative terminal. So just like I have a north pole and a south pole, okay, just like a north pole and a south pole, something similar to that, I have a positive and a negative side, and because of that there is an electric field. If I have a north and a south pole of a magnet, then there is magnetic field. So similarly here, because of the plus and minus, there is something called as electric field inside. So in a magnetic field, a ion particle will experience force, and in an electric field, who will experience force? A charge. A charge will experience a force in an electric field. Okay, so more about fields and the strength of the field and everything in detail will be in electrostatics. Okay, so because of this force, the electrons are going to drift. This is that extra energy which is being given, which we are talking about. Okay, so that is what we need to discuss today. Okay, find out what we call as the drift velocity of the electrons. Okay, we want to get a formula now, so we'll just note the formula for drift velocity. Okay, we will say Vd. Okay, small v suffix d here is d stands for drift. Okay, so what's the formula? It's equal to I, which is the current, upon NEA, small n, small e, capital A. Okay, these are the symbols. Okay, we are just noting down the formula. Okay, also equal to J upon NE. Okay, so clearly you can understand now this I by A. Okay, the N and E is remaining in the denominator, but this I and A has become a J. Okay, so again, what are these terms? Vd is the drift velocity, everyone knows. I is the current. Okay, what is this N? Okay, very common confusion mistake here which students make is N is not number of electrons. Please note, it is number of electrons per unit volume divided by the volume. Okay, it's number of electrons per unit volume of the resistor. E is a very common symbol in physics. Small e is the charge of an electron, which is 1.6 into 10 raised to minus 19 coulombs. Okay, it's a constant quantity. I'm sure you must have heard about it in school. Capital A is the area of cross section. Okay, area of cross section of the conductor. So you see, the previous case we had considered a cylinder. So the area of cross section of that cylinder. Okay, and J, which is I upon A, right? This I upon A is what we had substituted as J. That is what we call as current density, or to be more precise, we can say it is areal or superficial over the area, because it is current upon area, right? So areal current density, current upon area. Okay, so this is the formula for drift velocity. We are not going to derive it, we will just note it down, take it for granted right now. Okay, Vd is I upon NEA or J upon NE. Again, please note, keep in mind, N is not number of electrons, it is number of electrons per unit volume. Alright, so let's take a simple example again. So we are solving a numerical, so please remember data diagram equation. Okay, we discussed this in lecture 2. So they are saying that the magnitude of current density in a copper wire is 500 amperes per centimeter square. So check the units always. ampere per centimeter square. Okay, so it is current upon area, so it is definitely current density, so I will write J. But if you see the units, centimeter square is not SI units. Okay, so how will I note it down? I'm going to say, okay, the given quantity is J is 500, but then ampere per centimeter square should not be left as it is. So what we will do is centi. Okay, the word centimeter, right? So when I say centi is a prefix. It means 10 raised to minus 2. So it's not centimeter square. It is centimeter square. Okay, so what I'm trying to say here is that it is 10 raised to minus 2 square in the denominator. It is centimeter the whole square. So it is 10 raised to minus 2 square in the denominator, which when goes in the numerator, okay, minus 2 square is minus 4, which when goes in the numerator becomes plus 4. So it's going to be 500 into 10 raised to 4 amperes per meter square. Okay, very important. By default, you should develop this habit of writing all the numbers in SI unit, okay, in the data itself. Okay, what else? So we'll continue reading. Please note, we are not going to read the entire question, slowly, part by part. Okay, so if the number of electrons per centimeter cube, so that means they are talking about the number per volume, right, per unit volume. So again, we will note it down as small n, and it is 8.47 10 to the power 22. But again, since it is centimeter cube, okay, which is not the SI unit for volume, we will use it as meter cube. So again, centi is 10 raised to minus 2, 10 raised to minus 2 cube will become 10 raised to minus 6, which will go in the numerator, right? Centimeters was in the denominator, so it goes in the numerator. It becomes 10 raised to plus 6, and I already have a 10 to the power 22, so I'm going to make it as 10 raised to 22 plus 6 will give me 10 raised to 28. Okay, so that's my number of electrons per unit volume. Okay, calculate the drift velocity of the electrons given the charge of electron. Even if it's not given, we should know this number. E is 1.6 10 raised to minus 19. And what are they asking us to find out? It is the drift velocity, so Vd, and we already know the formula, right? We need, you need to have a football if you want to play the football. So it's J upon Ne. So let's just plug in the numbers. Okay, J, we are going to use it as 500 into 10 raised to 4 divided by N. What is the value of N? It's 8.47 10 to the power 28, and E is 1.6 10 to the power minus 19. And welcome to your first formal calculation where you are going to require logs. Okay, that is the reason why I started the whole 11th standard with log. Okay, in most of the chapters we need to do such kind of calculations. Okay, so please, you can pause the video here. I am not going into the details of the log again. Pause the video here, calculate the answer, okay, using logs. Please make sure numerator is more than the denominator, all numbers are more than 1, okay, and we should have 4 digits. And if you do the log calculation, okay, please, you can again pause the video here, find it out, just solve it over in your notebook, and you should get this final answer. Okay, it is 3.69 into 10 to the power minus 4 meters per second. This is the speed of the drift velocity of the drift speed of the electrons. Okay, all right, so now that was just a simple example. Okay, more are there in the homework you can solve. So we'll go to the next topic in the chapter, which is quite colorful and very simple. Okay, it's color coding of resistors. Okay, so that's a resistor there. Okay, this is how resistors look like. This is just one type of resistor, and the most commonly discussed resistor is the one I'm showing here. Okay, it's very tiny. It's just hardly maybe 3 or 4 millimeters in length and maybe 1 or 2 millimeters in diameter. Okay, if you want to know more about what are the different types of resistors, okay, what are they made up of, okay, and more details, about all these Ohm's law and more, just some simple easy to understand basics, I would recommend you go to this website. Okay, the link for the same is also there in the description of the video. Is just extra information if anybody would like to know more. Okay, but this is the most basic type of resistor that we are going to discuss about today. So what do we want to do here? Okay, so you see the number was color coded. The value of the resistor was coded in the form of colors, and that's what we need to learn. So this is the most common question which I face from students whenever I introduce this topic, is why can't they just print the numbers instead of the colors? You see there are colors here: green, blue, orange and gold. So they have anyways printed this whole ring around resistor. Can't they just print the number? Okay, why are they encoding? It's like a form of encryption. The value is encrypted. You can't just look at it and know it. You need to know the science behind it. Okay, or at least the way to find out the number. So what is the reason for doing this? First of all, it's very easy. Okay, it's very easy to print a ring, okay, around any cylindrical object. It's very simple to do that instead of printing a number. Okay, so the manufacturing process is easy. Okay, this is not the only reason. This is just to begin with. Okay? You just have to print the same color all around the cylinder, which is very easy because of the shape. Okay, what if I give you a big packet of resistor? You see there's several, like maybe 150 or 100 resistors in this plastic bag. Now if I tell you, give me a particular value, let's say 5 kilo ohms. Okay, how are you going to pick up every resistor and see in detail as to what is the number printed on it? Okay, so from a distance, if you are observing from a larger distance, it will be easy to identify the color rather than identifying the number, looking for the correct, if you're searching basically in a bag of resistors, it will become easier. Okay, another thing, when you use these resistors in a circuit, okay, so this is this white thing behind is called as a breadboard. Okay, because it has these perforations, okay, wherein you can put these components, and this small green thing here is what we call as a printed circuit board. Okay, PCB in short we say. Okay, so when these resistors are to be put on the circuit board, okay, if they were not color coded, okay, I will have to read the numbers only from a certain angle. Whereas color codes, which are printed all around the resistors, right, so you can just pick up the board and just turn it around, and you know if you are reading the number, it will be quite challenging. But if you just have the board in your hand, you can just see the colors, and you will know the value. Okay, so again, the point here is that for us it may be challenging. It's not going to be very difficult, but at least we have to learn how to decode, right? The color is coded, so we need to learn how to decode. But for those who are dealing with these components day in and day out, right, if you just go to Lamington Road in South Mumbai, right, everyone knows. So all these, there are lots of shops there where they sell these electrical components. So for such people who are on a daily basis dealing with them, for them identifying with colors is actually easier. Okay, there is always a chance of the numbers fading out, and if the numbers get faded out, if they get erased due to whatever reason, okay, and if you use the wrong resistor, right, because you had calculated before you put them on the circuit, always things are calculated. Okay, the resistor, what resistance should be there, and then accordingly you have to choose a certain resistor. So all your calculations will go wrong if you use the wrong component. Okay, but if there is an entire ring which is printed around the resistor, then the chances of it getting faded away will be quite less. And even if it does in one particular spot, then you can always see you can just turn around the cylinder and always still be able to identify the value correctly. Okay, so chances of errors would also reduce. Okay, so now let's decode the numbers. Okay, so this is a table here which we are going to use for decoding. Okay, so you can see here on the left we have all the colors. These are the colors which are possible. Okay, starting from black, brown, red, orange, right, yellow, green, blue, violet, gray, white, gold, silver, and then there can be no color, means no band. Okay, so please note the difference between gray and silver. Okay, They can look alike. Sometimes gold and orange also can be confusing, or orange and brown. Okay, so please be careful about that. And let's say a resistor is given to us with these 4 bands over it. Okay, so you can see the first one, right? The first band, it denotes, it gives me, right, the first digit, which can be from 0 to 9. Okay, so here, which is my first color here? You can see what is the first band. Can I say it is brown? Okay, you see, just match the color, it is brown. And what is the number next to brown? It's 1. So I'll just note down 1. Okay, what's the second band here? Okay, can I say it is very similar, looks like violet? And for violet, in the second digit, and even the first digit for that matter, what's the number? It is 7. So it is 1 7. I got my first 2 digits. What about the third digit? The third is not a digit. The third ring, okay, the third ring here, it's a multiplier. That means it is giving me a power of 10. So you can see here, okay, it matches with orange. And orange in the multiplier would mean 10 raised to 3. If it was orange in the first 2 digits, then it would simply mean 3. But now it means 10 raised to 3. Okay. And the last one here, okay, is gold. Okay. And it gives me the tolerance range. So for the last one, I can only have either brown, which means plus minus 1%, red, plus minus 2%, or gold, which is plus minus 5%, silver is 10%. And if there is no ring at all, okay, no color band at all, no color, then it is plus minus 20%. Okay, these are the 5 bands possible in the last ring. But please note, this is just as per our textbook. If you just search on Google, okay, color coding of resistors, you will see all these colors also, for which we have not written any tolerance value. Okay, they are also there, like 0.1%, 0.2%, or 0.05% tolerances are also there. But as far as our syllabus is concerned, we will just need to know these 5 tolerance bands. Okay, 1, 2, 5, 10 and 20. Okay. And again, if you check for color codes on Google, you will notice that, you see, the example I am using here as per the syllabus, okay, NEET and JEE syllabus, is of 1, 2, 3, 4 bands. But you can have 5 or more bands also. Okay, and their color coding would be slightly different. Okay, the basic principle is the same. Okay, but we just need to know how to decode 4 color band resistors. Okay, so here 17 into 10 is to 3, and again gold is for plus minus 5%. Okay, or in other words, what I can write is 10 is to 3 is nothing, but usually we express in kilo or mega ohms, so we can say it is 17 kilo ohms plus minus 5%. The value can vary, either more, 5% more or 5% less. Within 17 kilo ohms is what you can expect from this particular resistor. Okay, let's take another example. So now I have a second resistor. The colors are red, blue, green and silver. So we have our table ready. First band here is again red, which is the number 2. Blue is for number 6. Green, the multiplier is 10 raised to 5. And silver, the tolerance is plus minus 10%. So again, 10 raised to 5, what I can do is, if I want to express it as mega ohms, okay, then I can write it as 2.6 mega ohms, right? 2.6 into 10 raised to, mega stands for 10 raised to 6, like kilo is 1000, so mega is, 10 raised to 6. So 2.6 into 10 raised to 6, right, will be nothing but 26 into 10 raised to 5. Okay, so I can write it as 2.6 mega ohms plus minus, again it's silver, so 10%. Okay, so that's the way to understand, to decode. Okay, let's take one more example here. So I have red, white, okay, and that looks like brown and gold. So again, red is 2, white, okay, see the white band is number 9. Brown is again, I can see as a multiplier, as a digit it's 1, but as a multiplier it's 10 to the power 1. and gold we already know it's plus minus 5%. So what is 10 is to 1? 10 is to 1 is nothing but 10. So 29 into 10 is 290 ohms, right? So 290 ohms plus minus 5%. So as I said, it's quite simple. Okay? You just have to note these numbers. Okay, what about the reverse way? The bands are not given to us. So, okay, they can ask you this also in the exam, okay, in the questions. They won't give you the bands, they will give you the number. They are saying it is 4.7 kilo ohms plus minus 10%. What should be the colors? Okay, so first of all, the first digit here is 4. And for the number 4, I know the band should be yellow. Okay, so that's fixed. Now you see, we don't want this decimal here. Generally, it's just the first digit and second digit. It's not first digit point the second digit. So if I want to remove the decimal, okay, can I say it is 47 into 10 raised to 2? So the idea here is the second digit is 7, which would be in this case violet, and kilo 10 raised to 3 has now become 10 raised to 2 because I wrote 47. Okay, and 10 raised to 2 basically would mean now the third digit would be red. And plus minus 10% you can see in the table, plus minus 10% is nothing but silver. Okay, so I get my 4 colors. If it is 4.7 kilo ohms plus minus 10%, it's going to be yellow, then violet, red, and silver. Okay, let's take one more example for this, for you can say the reverse of the coding. Okay, 3.9 kilo ohms plus minus 5%. Okay, so first digit is again 3. So where is the number 3? It's for orange. Second digit is number 9. And where is 9? 9 is white. The multiplier, now you can see I have removed the decimal. It's not 3.9, it's 39. So I will say 10 raised to 2. 10 raised to 2 is again red. Okay, the multiplier is going to be giving me the red color, red band, and plus minus 5% is gold. Okay. So again, this is very simple to understand, but you may ask, what about this table? Okay, how do I remember these numbers? Okay, or especially, see, the numbers are easy: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the same here, and the same here is the power of 10. 10 raised to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The last two you can remember is 10 raised to minus 1 and 10 raised to minus 2. Okay, and the tolerance is also fine. What you really need to remember here is the sequence. Okay, so to remember the sequence, there is a very common mnemonic. Okay, what do we mean by mnemonic? Mnemonic means something which can help you to memorize. Okay, it's a statement which can help you memorize something else. Okay, so what is the mnemonic going to be? So we will just use the first letter for each color: B for black, B for brown, R for red, O for orange, Y for yellow, G for green, B for blue, V for violet, gray, white, gold, silver, and N for no color. Okay, fine. So what is the mnemonic here? Very simple. It's B.B. Roy of Great Britain. Okay, has a very good wife with gold silver necklace. So you see, I have kept the font size more for the main digits, for the main colors here, right? Black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and no color. I mean, I'm just writing no color with black, but no color is not black. Okay, no color means it's not there. So the sequence can be very easily memorized with this statement: B.B. Roy of Great Britain has a very good wife with gold silver necklace. Okay, this is the most common mnemonic actually used for color coding in India. Okay, B.B. Roy of Great Britain has a very good wife with gold silver necklace. If you check on Wikipedia, right, there are more than 40 different, you won't believe it, 40 different mnemonics for color codes of resistors. Okay, resistor color coding. So you can just go through all of them. Okay, but this is the one which is, even Wikipedia mentions that in Indian classrooms, most commonly this is the one which is used. Okay, B.B. Roy of Great Britain. In fact, it's there even in our textbook. B.B. Roy of Great Britain has a very good wife with gold silver necklace. Okay, so this is all about color coding. Please note Okay, color coding is not essential. You can also use this device, okay, this yellow device with this knob here, and there is a screen. This is what we call as a multimeter. And all of you, once your college begins, which we don't know when, after the lockdown gets over, okay, but in your practicals all of you are going to use this. Okay, you are going to see this being used in your practicals, physics practicals. This is called as a multimeter. Why? It measures multiple things. Like, if what do we call as a thermometer, right? It's a meter, it's a device which measures what? Temperature. Thermo. What is ammeter? Okay, it's a meter which measures ampere. Volt meter, right? It's a meter which measures voltage. So this is multiple meter. It can measure multiple things. Okay, you can see here on the knob, you see it can measure on this side. Okay, it is voltage, you see, V. On, if you turn the knob on this side, on the right side, it is amperes. Okay, then there is resistance here in green. Okay, and like that it can do few more things also. So that's why it's called as a multimeter. So you can actually practically use this also if you don't have the color coding, and if is a resistor which has no color codes, because there are several other types. Okay, not all resistors are cylindrical like this. So this can also be used. Okay, it's just a note. Okay, so that's all for today. So please do the homework, and you can contact me if there are any doubts. So I hope you liked the lecture, and on Monday now we will continue with the next lecture. Okay, thank you. Bye bye.